As many of you know, AGS has been leading the cause for geography and now geospatial science for over 167 years. Throughout that time, some of the most important figures in our national history have held positions of leadership in AGS and had an important impact on the field of geography and at the highest levels of national public policy. Our most recent history has allowed AGS to pivot from supporting pure geographical research and exploration to now embracing the world of geospatial science, which also, as we know, is pretty much ubiquitous in our lives. AGS would not be able to do what we are doing right now if it weren't for three people who have guided it for a combined total of 91 years of service. We thank Chairman Emeritus John Gould, President Emeritus Jerry Dobson, and Executive Director Emerita Mary Lynn Bird for guiding AGS for so many years and for continuing on with us now to keep AGS true to its mission. Unfortunately, John and Mary Lynn are unable to join us this morning, but Jerry is here to represent them, and Jerry, we want to thank you.
Thank you. Thank you.
And now we move to a topic that is of particular interest to many of our members, geospatial technology and energy. And to lead this discussion is our President Emeritus, who you might not know, but was one of the first scientists and pioneers to study GIS and realize its power to change our lives. So Jerry, it's very appropriate to have you up here today. We're looking forward to hearing from you and your panel.
Thank you. On behalf of the American Geographical Society of New York, it is my pleasure to welcome you to this plenary session. AGS was founded in this city by leading statesmen, mercantilists, abolitionists, jurors, and geographers who understood the true value of geography in business, government, science, and society. How fitting it is that we meet today in Low Memorial Library, named after Seth Low, second mayor of the Consolidated City of New York. At the time of his election, this outstanding New Yorker was the sitting president of two venerable New York institutions, Columbia University and the American Geographical Society. AGS has been a vibrant part of the city and state of New York since 1851. Franklin D. Roosevelt was a member of our council when he was elected governor of New York and president of the United States. For 167 years, AGS has been a leading advocate for geography in the United States and around the world. Our mission is to advance and promote geography in business, government, science, and education. Thank you for joining us as we look ahead to the future of energy, viewed through the perspectives of geography and analyzed through geographic information science. Energy starts with physics and chemistry, but the rest is geography. Where is the supply, where is the demand, and how does it get from one place to the other? How does human geography drive production, use, substitution, waste, and myriad transformations from one form to another? How does economic geography, why people do what they do, where they do it, impact primary production, transportation, goods, and services? How does energy production, transport, and use impact environments at every stage along its way? GIS is the essential methodology for studying anything that involves locations, movements, and flows, and that pretty much describes energy. I spent the first 26 years of my career at Oak Ridge National Laboratory, then owned by the Energy Research and Development Agency, which later became the Department of Energy. First, I was in the Energy Division, and then the Geographic Information Science and Technology Group, one of the founding centers of GIS, a clear sign of the link between energy and geospatial. My early research focused on energy. My first project was to evaluate one state's innovative but impractical plan for siting a cluster of nuclear generating plants. Then for several years, we assessed water availability for energy. In 1979, geographer Alf Shepard and I answered a central question for the U.S. economy. Would the nation's rivers be adequate to cool the fossil and nuclear generation capacity considered essential over the remaining decades of the 20th century. Geographer Bob Honey presented the results to President Jimmy Carter in person. Mr. Carter's administration was famous for using all sorts of development scenarios to review energy policy decisions. For a while, ORNL became a geographic simulation center for one energy initiative after another, coming out of the White House. We did a lot of technology assessment as well, testing, for instance, the ability of the country to meet county-by-county production goals from solar and other renewable energy sources. Next, the group I led was responsible for citing coal production goals for federal lands. We helped Liberia write a national energy plan during the disastrous reign of Sergeant Doe. Later, at the University of Kansas, I led a privately funded project to screen the state of Kansas for suitable wind farm sites. Our panel today consists of eminent experts at the nexus of energy, geography, and geospatial. Geoff Zeiss believes we need to get serious about improving our knowledge about the location of underground energy infrastructure. Not knowing is not only hazardous to the public and to workers, but represents a major drag on the build-out of future energy infrastructure. Kuman, Navulur, says satellite remote sensing technologies provide global perspectives for sustainable energy initiatives, including biofuels and solar, as well as hydro. Bill Meehan says transformation of the energy infrastructure requires rethinking conventional behavior by using technology in new ways. Koeln advocates geospatial technologies for monitoring the changing world, for understanding energy consumption, and for increasing our use of renewable energy resources. Rodney Buhrsmith explains access to energy, a real-world GeoEnt example to predict future hotspots of instability. Our first speaker is Rod Buhrsmith. He heads the business development at Eastview Companies in Minneapolis with a specific focus on GeoEnt. He has spent 11 years with Eastview, and prior to that was with Thomson Reuters, where he led the law school division. Rod has an undergraduate degree from Georgetown University and MBA from the University of Louisville. Rod?
Thank you. Thank you, Jerry. Good morning. Good morning. Good morning. How's everybody doing? Hey, Lee. All right. Most of us here are representing industry, and industry has a factor that academic does not, government does not, and that is we care about quarterly results. I'm a small company. We care about annual results. We're not looking at quarterly earnings. But annual is this very, very short period of time. And so what we have to make money on has to actually answer problems today. So today I'm starting with probably the most, or the least far, or the most far from 2050. But it has actually great application, and what's being done with this technology will only grow and portend for 2030, 2040, 2050, what needs to be done to predict where hot spots of instability are throughout the world. Some of my comments will follow on from Director Cardillo yesterday of the NGA, because really what Eastview does, what I do, is in great support of what the NGA is doing. So the outcomes today. You're going to learn some of the things that many of you already know, that certain authoritative providers like the IEA and the World Bank says about access to energy. And then I'm going to introduce a predictive model, an actual platform called Glimpse that Leidos has developed and that the NGA already uses. They've been using it for 3 years. It makes predictions into the future up to 5 years, about in 2,000 square kilometer increments. So you think about the world, 2,000 square kilometers is still quite large, but compared to the world, it's quite small. And the granularity of that will continue to increase as data becomes available. And then, really I would say the theme of what I'm talking about and what Eastview does, we're a source supplier, is applying all we know until we know more, and then keep reapplying. And that's definitely a theme of my comments. Oops. All right, so I won't read these. I'll leave them up here for a minute or so. These are the facts. This is the context. This is the scale of the problem, and in some cases, the scale of both the opportunity and the success that's being realized right now in developing countries around the world, our developed country, of course. You see from these that the second one in particular, the 193 member states of the UN put a specific goal forward to ensure access to affordable, reliable, modern energy for all by 2030. And what you'll see from the Glimpse platform, access to energy as displayed via night lights, as conflated with land scan, population growth. Access to energy, as we've heard for a couple of days now, is one of the, I would say, along with access to water, perhaps access to education, access to energy is a strong causation, if not correlation, to where people are unstable, where there is hot spots of concern, there is poverty, not enough infrastructure for housing. So all of the basic needs that I haven't spent really much of any time of my life not living without, the majority of the world lives without every single day. And that, when I prepared for this and have been listening to the conversations, it's hard for me not to be, to feel really heavy about that. I was so happy we started today with some of the innovations coming forward, because those are very promising. The innovations that truly leapfrog, not that are incremental. This slide Dr. Pasqualetti put up in his first day, and it shows how in the next 20 years, up to 2040, energy demand's going to increase, not a surprise. It shows the scale of it, and that's nice to see. But this is a problem that is for all of us to solve. And someone yesterday, I think it was Dr. Nathawani, I'm sorry if I pronounced your name wrong, it's falling on deaf ears. It's falling on deaf ears of our policymakers, and really of us as consumers and individuals. NGA, as an example, I think one of the things that they do that is extraordinarily formative and fundamental for solving the problems is making data available. And yesterday, Director Cardillo showed a gravity model. He discussed a global bathymetric model that they're working on. He showed DEMS over Antarctica and the Arctic. From my standpoint, from Eastview's standpoint, we can only solve these problems, well, not only, but one of the fundamental things is access to information. And not just regional information. We need the investments and the collaboration and the inspiration to create global models that can be exploited by many of you in the room that need data to solve your hypotheses, to put a policy statement in writing. And so, in my view, the more authoritative, the better, the more coverage, the better. Problems happen at a local level, but what we're seeing here is the grand scale of how it's all interconnected. And I think we know in our minds the level of interconnectivity that we feel using the internet as a great example. But we need more data that allows the analysis to connect through the whole system. And that takes money, it takes collaboration, interdisciplinary collaboration. And then the last point, the more archives, the better. And the reason that that matters, as Landscan will indicate, is as you have years after years and soon decades after decades of archived information, authoritative information, it starts communicating the trend lines and communicating what needs to be communicated in ways that single snapshots in time, of course, cannot. So Glimpse, back to my original statement, we have to create things that solve problems today. that customers will pay for today. And so GLIMPS, which it stands for down at the bottom, Global Monitoring and Planning System, it's a platform that predicts instability. It enables, at the moment, NGA, who's the GeoEnt broker for the USG and actually has influence well outside the United States government. It allows them to prioritize their procurement and creation of data. And so by that I mean, you would think NGA, and with all the satellite imagery we're going to hear about, like, we've got all the data covered. It's all over the world. And of course, in the first day, we heard how difficult it is to process through that. Well, we don't even have all the data, far, far away from that. And so it allows NGA, there are certain parts of the world, many parts of the world, the majority of the world does not have foundational GeoEnt data in place. And there's different arguments or different debates on what is foundational GeoEnt. But at the very basic level, let's just call it 50K topographic mapping data. So the 1 to 50,000 scale is a fundamental GeoEnt data layer, and it is absent in half of the world. And NGA is the entity that's trying to fill that gap. So GLIMPS is one platform that allows them to do that. It provides anticipatory intelligence, and NGA has a mission to stay ahead of the curve, in some ways define the curve. And so a platform like this, and there are other platforms. I mean, this is a predictive model, so let's just call it generically what it is. It's a predictive model. You all are building and have built thousands of predictive models in this room, and you don't build them just for the sake of building them. You do them to affect decisions. And in this case, the decision that gets effective is where to fill in some of the foundation geospatial data that needs to be done. I'm going to talk to you about a couple of the data sets. The source is really where we come from. And then the technical, I do not pretend to know how machine learning really works or algorithms. That's really not my specialty. But I know they do, because the output of what we see proves it. So there's two particular data sets of the 45 or so that the GLIMPS platform uses that really do tap into access to energy. We've seen night lights up here. This is a relatively new data set in its global composite. So night lights has been around for a while, but it's now in a state where it truly is exploitable by many of you. That's really important. It shows where energy is now. And Landscan, as Dr. Dobson mentioned, he was with Oak Ridge. He actually helped stand up the original version in 1998. It's been commercially available since 2000. And so it's a data set that, by show of hands, who has heard of or exploited Landscan? Many. And maybe I'm expecting to see a few more hands. Who has heard of or has exploited the Columbia University gridded population database? Actually, about the same. So these are examples of global data sets that have great funding behind them that are solving particular missions. Landscan's, I think, originally was nuclear plume analysis. So leveraging data to show us what and why. I'm not going through all of these. I just wanted to give you a sense of within GLIMPS, there's environmental, demographic, and economic data. I've talked about night lights and Landscan. There are many data sets. In fact, some of you may have some that if you're imagining or understanding what I'm talking about may be applicable to this platform. And then going forward to 2050, in my view, geospatial technologies, the art and science of GIS is just going to continue to expand, and I'd say that's been revolutionary for the environment since Jack Dagerman founded Esri and others before him. Access to authoritative data, rigorous models, computing power. These are all things that we should feel very bullish and optimistic about, because every one of those are developing at strong speeds. Collaboration, it's always worked between industry, interdisciplinary. And then, I mean, a picture shows 1,000 words. I mean, what we've been moved by aren't words on screens, but I think some of the graphics that have been shown during the last couple of days. And so visualization is at the heart of GIS.
Thank you. We will take time for just one question from the audience. Then there will be a block at the end for more discussion. Anyone have a question? All right, we'll move on. Just a hint to the other panelists, if you want more time, do what he did. Mention one of my projects in great detail, and you'll get the time. All right.
We mentioned 2 of your projects.
Oh, you're golden. Please welcome Dr. Greg Koeln of Radiant Solutions. Greg joined Earth Satellite Corporation, which is now Radiant Solutions, a Maxar Technologies company, in 1992 as their chief scientist. And I might note that I've known him all that time. We've been good friends. And is currently serving as Radiant Solutions Technical Fellow, leading research and development. Greg developed various new remote sensing and geospatial processing tools, including a unique change detection methodology which greatly reduces the cost of updating geospatial products. His degrees are in wildlife sciences from Colorado State University, Mississippi State, and Virginia Tech. He is most proud of being a member of Radiant Solutions teams that have mapped land cover globally for 4 epochs and annually updates global change. He calls himself a Landsat nerd and evangelist.
Oh, no, it's out there. Jerry, thank you very much. It's been great knowing you for all those years, so that could give me one more minute, I hope. I really appreciate that. I do have a secret, and Jerry sort of shared the secret with you a little bit, but I do have a secret that doesn't leave this room. I've been doing satellite remote sensing since the middle of the 70s. That's not the secret. The secret is, as you mentioned, I'm a wildlife biologist. I'm not a geographer. So that should not leave this room, the fact that I'm not a geographer. But I've been doing remote sensing, feeding, clothing, my family, sheltering my family, that got the kids through school by basically processing satellite imagery data. So that has been my life for many, many years. So let me get to the first slide. You know this slide far better than I do. We've got tremendous amount of change going on in the world, and most of my remote sensing work has been trying to map or determine where that change is occurring. This is actually a slide from one of my friends from Esri, Francis Kelly. He lent me this slide and the next, but of the 8.8 billion people by 2040, what I did not realize until I saw this slide is that 6 billion of them will be in the cities. And that's going to be quite a challenge. And this is a challenge that I really did not know, that in order for us to house that number of people, we've got to start building 1,000 buildings per day and spending 1,000 buildings per day and spending $3.3 trillion on infrastructure every year. What I've been doing, and my staff at Radiant Solutions have been doing, is trying to map that change. And we're doing it for the world, and we're doing it with Landsat and Sentinel-2 data. What we've done, and if those of you who have done mapping of change with satellite imagery, you know you've got omission errors and you got commission errors, and it's really challenging to do at times. What we found is helpful is to take a full stack of imagery, and you don't call it change unless that change actually persists for a couple of the next images that you have. What you're seeing now is actually an image of around Houston, and the bright colors represent the changes that have occurred through the last 32 years. So the blue areas are the changes that occurred about 32 years ago. The bright red and yellows are the ones that have just changed in the last couple of years. You notice the expansion from the city, from the center out, the typical halo type of growth that you have. This image is a DigitalGlobe image, and it's got the red dots or the red polygons over the various buildings. This DigitalGlobe image was a 2014 year, collected in 2014, but the more recent, I'm sorry, let me try that again. The image from which the footprints of the building were collected was 2014, but the image I have is a much more recent image. And you can see there's a lot of building footprints that just did not get captured because the 2014 image was used. We use our technique of change detection, which is called persistent change monitoring, to identify those areas using satellite image, Landsat and Sentinel-2 imagery that are out of date. So it's those areas that primarily are out of date. And then when you get to the more high resolution imagery, we can then just do pinpoint maintenance to update just the data that needed to be updated. This may explain the precision change model better. This is a natural gas field in Russia. It's hard to see maybe from these monitors, but in the far, far east of that image, there's a blue line going in. That line came in about 1988. It was the first road to go into that area in Russia. And then you can see the expansion of that natural gas facility throughout the years. We're using moderate resolution worldwide to look at these changes. Using that moderate resolution, though, isn't going to tell us what the change is. So that's when we have to link in the high resolution imagery. So what you see on the left on that is you'll see the green area that shows the change, and then you'll see the DigitalGlobe image that is being used to actually characterize that. So we use the PCM product, the change detection product from Landsat and Sentinel-2, as a tipping and queuing mechanism for that. Not only is it showing us new developments out there, this is showing where the clear cuts are. And it's actually, so you can see in the blue areas, those are the blue areas that were clear cut in 1980, and the red areas are the more recent clear cuts. But not only is it showing you when it was cleared, if you think this was in active forest management, you can almost assume that when the area was cleared, by the next year, that area was replanted. So if you look at the areas in blue, they are cleared in 1987. Let's assume they're planted in 1988. So now we know that those areas in blue probably have forest stands that are 30 years old on there. So we've been using persistent change management to map not only the clear cuts where they're happening, but actually then getting forest stage age out of that. We've gone persistent change management when we do it from the 1980s to the present. We typically use one Sentinel-2 scene, one Landsat scene per year. But when we've been trying to look at the changes in water levels of reservoirs for irrigations, reservoirs for hydroelectricity, we take a much larger stack of data. This particular stack, we had over 300 Landsat scenes in this stack. And now we can start looking at what's the probability that that reservoir is going to be full. If you look at the magenta area in the sort of the middle, that's the area that indeed about 100% of the time you can expect to see water in that part, small part of the reservoir. You get out to the red and yellow areas, and less than 1% of the time does that reservoir ever have that type of water. That's really helping us understand what water is available for irrigation and for hydroelectricity. Let's look at wind. Not only are we going ahead and mapping the changes in the world, we're using the geospatial technology to help forecast how much energy, how much wind's going to be produced, how much energy we're going to get from the turbines. So this graph is actually showing the difference between what we're forecasting from the turbines, from a whole series of turbine farms, wind farms, and with the actual. So the green line in there shows what we forecasted, the amount of energy that would be produced up to 24 hours ahead of time. And then the red line shows the actual energy that was produced for that time period. We're using machine learning to take the data, take the deltas that we have, and then reapply the machine learning on that to constantly improve the model. So every day, that type of forecast starts getting better. We're using land cover, we're using topography to help understand where the winds will be, what the magnitudes of the winds will be, and the like. Looking at heating degree days and cooling degree days, and you can see on the chart on the far left that the cooling degree days have certainly been increasing since the 1950s. 30% increase in cooling degree days in the United States since the 1950s. Heating degree days, you can also imagine, have been decreasing, but not quite as much as the heating degree days. If you look at the chart on the far right, look at that black line out there. Everything north of the black line in the United States has been actually using less energy to heat their homes and facilities, but everything south of that has been taking more energy to cool their homes and the like. Unfortunately, it's been a net loss. Overall, we're using even because you're spending more energy on cooling than on heating, so it has been a net loss. We also have models out there that forecast the cloud's positions at 5-kilometer resolution for the world. So for the whole world, for 30 days out. Admittedly, the skill of forecasting where the clouds are 30 days out is challenging. But within the first 15 days or so, it's very, very good. So solar farms are buying our forecast of the clouds. And this is just our silly things that not only were we forecasting the clouds, but when we had the eclipse last year, we saw the effects of the impact of the eclipse on the energy that could be generated from the solar farms. And then this is an area for the southwestern United States where we combine our forecasts for 9 days, showing what we'd be forecasting from solar. So the solar are those daily humps of data you see there. Some of the humps are larger than the others because of our cloud forecast. And then the amount of energy that we're forecasting from wind generation. And again, that's based upon the climatology, it's based upon the terrain and the like. So that's some of the things that we've been doing using geospatial technology to look at where the energy demands are, where the energy demands are changing because of new construction, and then the geospatial technology to improve our forecast for the use of renewable energy. Thank you.
Are there any questions for Greg? Okay.
It let me off easy. That's good.
All right. Our next speaker is Mr. Bill Meehan of ESRI. Bill is the Director of Utility Solutions, responsible for the messaging, marketing, and positioning of ESRI's GIS software to the electric utility industry. He is a registered professional engineer who received his BS at Northeastern University and MS at Rensselaer Polytechnic Institute. Bill is the author of 4 books on GIS and the electric utility business. He has published hundreds of articles and blogs. Prior to joining ESRI, Bill was the Vice President of Electric Operations of a major electric utility in the Northeast. He is most proud of taking complex concepts and making them easy to understand. Bill?
Thanks. What's the weakest finger in your hand? Come on, let me see them. The pinky, right? And what's the most popular letter in the alphabet? Anybody? Hey, that's right. So tell me this. Why is it that the original designers of the keyboard chose to put the most popular letter A in that awkward position to be struck by the baby finger? Why did they do that? Anybody? I heard somebody. Does anybody know? To slow, yeah. The original designers of the keyboard put the popular letters in easy to get to places, right? But remember, what was the original keyboard but a mechanical typewriter with all these levers, right? So as people got used to it, the letters all jammed up. So what they did is they put the popular letters in hard to get to places so they could slow the typist down. Well, we have electric keyboards, we've had them for years, and yet we still continue with that legacy process. Why do we do that? Well, is it because we don't want to change? I don't think so. It's because I think we have a blindness to things. We just don't see things anymore. We become so used to it. And there's a term for that kind of blindness, and it's called scotoma. And what it is, it's a medical term and a psychological term, but it's kind of like tunnel vision. But it really means failure to see what's before our very eyes. It's a scotoma. So when I think about the world today and how we need to transform, we need to peel away those scotomas. And I believe that all innovation and transformation occurs when we do that. So how many people here have heard the term digital transformation? Okay? So there are really two pieces of that. The first is you have to have the technology in place, right? But then also you have to be able to change people's behaviors. So it's kind of like that to really create innovation, technology has to be configured to change behaviors, and not just the little ways, but in dramatic ways. And I'll give you some examples. A little pop quiz. Does anybody know what this thing is? What is it? Yell it out. A Sony Walkman, right? And what was inside here was a cassette tape. And the cassette tape is analog, right? It's analog. All right. So what replaced the Sony Walkman? The Sony Discman, right? This was analog. This was digital. So let me ask you this question. When I went from the Walkman to the Discman, was that digital transformation? Everybody. Loud. There's only two answers. No. It was what I like to call digital transition. And because when we went from the Walkman to the Discman, even though we went from analog to digital, we didn't really change our behavior, right? You still collected, instead of collecting cassettes, you collected CDs. Remember, they're all in your glove compartment and there are boxes in your garages. So what really was digital transformation in the music industry? Somebody, I think, Spotify, right? So if you want to hear a song, you don't have to go in your garage and poke through boxes of CDs to find, you know, the third cut on the Abbey Road album, right? You just said, hey, Spotify or Alexa, play this song. So that really is transformational. And when I think about the energy future today, we need to peel away that scotoma and see things that we haven't seen before. Failure to see what's before our very eyes. So kind of another pop quiz. Well, I just did that one. So here's digital transformation. But I coined this term digital transition. That means that that's what, when we went from the cassette to the CDs, it was a kind of a transitional thing. And I think in many cases, we continue to do this sort of transitional thing and call it digital transformation. So I ran electric operations for a power company, and I was the pioneer of an early GIS at a utility. And so what is this? This is a map that was produced in 1927. So what did we do? We converted that map to GIS. And guess what? I forget how to go backwards on this. Is it the lower button? They said the top button explodes something. All right. So when we converted from the old maps to the GIS maps, we just converted the maps. They looked exactly the same way, right? And people just love the old maps, so we want to make sure they look exactly the same. You see that little rip? See that little rip over here? Maybe we should create a symbol for that rip. You know, because people are so used to it. Or maybe a coffee stain symbol. So the notion of that was kind of a digital transition. But GIS is not about maps. GIS is about discovery. Discovering how I can peel away that scotoma by seeing things in a different sort of way. That's what GIS is all about. That's what spatial technology is all about. Not only did we, when we converted those paper maps to digital, what did we do? People took them and they printed them out. And they stuck them on walls, just like the old maps. When in fact, it's really not about printing out, it's about maps. It's about changing the way we do business. And that's really digital transformation, changing behavior. So that's what we have to really continue to do. So, how many people have heard the term smart grid? Well, I just heard this morning, we don't even need a grid. Or maybe the grid will disappear. I just remember a situation when my granddaughter asked me a question, and she calls me Pop. She said, Pop, when did you and Nana meet for the first time? Or when did you ask for a date for the very first time? And I said, yeah, I remember calling your grandmother on a phone, in a phone booth in Harvard Square in Cambridge. And so Gloria said to me, Pop, what's a phone booth? So I think the idea is digital transformation and using things that we We just sort of transition. So smart grid is really good. I'm not in favor of smart grid because spatial technology is really involved there. So, but what happens though when we get this smart grid and all of a sudden Mother Nature comes along? I don't think Mother Nature cares that we have a smart grid. It takes it down. So as we think about the grid, the energy delivery system of the future, we can't just apply digital transition to it. We must really think outside the box. And one of the things that I like about working in the GIS business is that it's all about really new technologies, that technology can be configured to change behavior. There are two things about GIS that I really think is revolutionary. One has occurred a long time ago, and another has occurred within the last couple of years. In the last couple of years, it's called a platform. Now, in the old days, when people did GIS, it was kind of these departments, and they had all this data on files and all this kind of stuff. Today, GIS is really available to everybody through a platform. How many people here use Facebook? Yeah, right. So when you take a picture, or when my daughter takes a picture of my granddaughter doing something cute, I see that picture the second after she does it. So the idea of a GIS platform is that when you do something now, it's available to everybody who needs it now. So the idea of really the transformational aspect of spatial technology are the two things. One is that it's a platform. And the other one is the more conventional part of it, which is spatial analytics, which is, again, it's not about making pretty maps. Pretty maps are great if they communicate. But it's really about discovering something. And now, with the platform technology, you can get data from literally anywhere. You know, from space, from LiDAR, we have a lot of real-time systems in the utility business. Now I can take that real-time data right now, and I can take demographic information right now, and I can take tweets right now, and put it all together in a GIS right now without having to store any of that data. It all comes from web services. And I can discover something that I was not able to see before. So GIS is this whole thing of a platform plus spatial analysis, you know, the ability to see patterns and to be able to predict. Imagine now that instead of having just the data sets that I can work with, that my whole world of data is open up to me. So I would just close by saying that GIS has the ability to provide huge understanding of the world around us so that we can attack these problems. And the idea of a scotoma is let's think differently about GIS. Let's peel away this thing so that GIS can liberate us to be able to solve the world's problems today. Thank you.
Please join me in welcoming Dr. Navulur, Senior Director of Business Development at DigitalGlobe. Kumar received his PhD from Purdue University. He has over 23 years of experience in the geospatial industry. He is the president of DigitalGlobe Foundation, which focuses on building geospatial capacity around the world. He is a board member of the Open Geospatial Consortium, a standards body for location data. He is the author of the book entitled Multispectral Image Analysis Using Object-Oriented Paradigms.
Thank you, Jerry. Bill, that was awesome energy. Next time, remind me not to go after you. There is a story. Actually, I grew up in India, and when we talk about energy, this is, again, 25 years ago. I lived in a small town. In summer, we would have power outages in summer when it's 100 plus degrees outside, at least 2 hours in the morning and 2 hours in the afternoon. So with the statistics that showed 600 megacities holding 8 billion people or whatever, that problem is going to be exaggerated. So we need to think about how are we going to support the community going forward. So appropriately, 2050 is not that far away when you start planning for these kinds of things. So I represent DigitalGlobe, another Maxar company. And I'm going to talk about how space-based technologies can be used for sustainable energy initiatives. So actually, this was a couple of years ago. There was a politician in India who actually was talking to me about the energy goals they have set up for India. They are very aggressive. They're talking about some 120 gigawatts of power they want to produce. And today, they are around 60 or 70. So they are looking at all possible sources of energy so they can meet this existing demand. I think India is around 1.2 billion people and project to pass China pretty quickly. And then the same concept of urbanization is happening everywhere. So this is a real problem, and there are several examples, both in Europe as well as Africa, where countries are trying to plan how do we meet the energy demands of the growing population as well as urbanization. So when we talk about that, the way I look at it is, first thing we need is data. So think about the coverage. 5 years ago, we had data. I think today, just with DigitalGlobe, we are mapping the entire planet around 8 times a year. And then when I see at the new space economy, the number of satellites that are coming along, it's just, again, I've been in this industry for 23 years. It's very exciting. And there are multiple resolutions, and from a DigitalGlobe perspective, our next generation satellites, we call them Worldview Legion, combined with our existing constellation, can come back 20 to 40 times a day. So data is not your issue. Data is going to be there. The next one is, which goes back to context. It's not about a data, but a single point. You need to think about, can you have that kind of data globally? I think those data sets are here, and I already talked about the refresh aspect of it. And why space? And space, for me, actually provides the best vantage point for our changing planet. So satellites, today, most of them are in the sun-synchronous orbit. They go from pole to pole. And the future, you have inclined orbits, very similar to International Space Station. So you will have lots of data to start looking at Earth multiple times a day and start addressing some of these energy issues. So when we started looking at, again, these are some of the projects we have done. The couple of ones I have not touched upon are geothermal. Satellite imagery cannot do much. I live in Colorado, where geothermal is really big. And then the usual oil and gas, which I'm not touching upon. But solar. Recently, we finished a project for the entire continent of Australia, where we mapped every single building and every house with the solar panel on it. We used digital elevation models created from the satellite data to do those 3D models, and I'll show you some examples. Now, not only you can identify which roofs have solar panels, you can actually compute the PVC potential of each of the rooftops. That technology is here today. So we did a couple of projects with the IDP camps in Syria, where we worked with some of the NGOs where they were actually setting up solar panels. So that's the fastest way you can get energy to the IDP camps. So solar has a lot of potential. The other one, again, this is an example from India, is biofuels. They're looking at different types of grasses that actually enable biofuels. And remote sensing, especially when you have spectral bands like red edge band and the near infrared bands, they're ideally suited not only to identify where these biofuels are, but also what is the status of them, how much energy can be produced from them. Hydro, this is actually one of the projects I did now 10, 12 years ago at DigitalGlobe. Even with one shot, you can do simple mensuration of the water levels in dams. When the water levels are down, you can actually measure it, and you can compute how much storage each of the reservoirs have, which can be transferred into the hydropower capacity. And there are several dams. I mean, this is a big source of power across the globe. So now we have those technologies. You really don't need 3D for it, but you can use oblique shots or single images to do that. We did one project which was interesting with NRL, where our satellite, we have actually 8 spectral bands on Worldview 2. And it so happens that 4 bands are on one detector, the second 4 bands on a different detector, and they have a 30 millisecond difference. And when you're going 17,500 miles an hour in space, NRL was actually trying to use the delta in the image acquisition time to see if they can actually identify the kinetic energy of the waves. So this was a very interesting project I worked 4 or 5 years ago, and I think there is a lot of promise for that as the water levels keep increasing. I think we want to look at multiple sources of energy, and kinetic energy from ocean waves is something is definitely of interest. So here are some of the examples. When you start taking pictures from space, if I take this building from multiple viewing geometries, we can actually create elevation models. And I think I saw my ex-colleague Craig, who is with Rikon. They actually do 3D models with 3 meter plus or XYZ in terms of 3D models, 3D textured models anywhere on the globe. So this technology is already here. Actually, this is a model from Rikon. This is San Francisco, and not only we can compute the 3D models, now based on some of the things Greg talked about, we can compute the PVC potential anywhere in the globe. And this was the example I was talking about, the Australia, where now with the machine learning, I think one of the points I try to make is that people use AI and machine learning interchangeably. I think most of the time, I think what we're doing is machine learning. For me, artificial intelligence or augmented intelligence is when the machines start making decisions for you. So most of the time when we talk about satellite analysis, we're just talking about machine learning, where we are training the data sets and the machine is trying to figure out where those objects or features are. So now we have at scale, thanks to the cloud computing and cloud storage, we are now able to extract the different types of solar panels as well as the PVC potential, so you can start planning large farms in developing nations. This is a project I did in Syria. This was with World Bank, where we collected imagery over multiple years. And then we were actually trying to figure out where are all the potential biofuels are. This is during when the crisis where there was not enough electricity being provided, both in Syria as well as across the border. So we were able to identify how much agriculture is there and which portion of the agriculture was actually biofuels. And then as I already mentioned, just by single shots, you can do simple mensuration. One of the projects that was fun for me, I did now 5-7 years ago, was for Bloomberg. When you have these oil tanks, they have floating lids. So by just taking one shot and computing the delta, we were able to estimate how much crude was stored in Cushing, Oklahoma, for example. So the power of remote sensing allows you to look at the entire globe, and the frequency with which these satellites are going to come, not only just DigitalGlobe, but the entire remote sensing industry, you will have the data to look at the entire globe on a much frequent basis, and this is coming very, very quickly. And then the details, the context, we are collecting data at 30 centimeters, but you really don't need 30 for all applications. These kinds of context of the entire planet is already here and will get much, much better for looking at sustainable energy sources going forward. Again, these are the digital elevation models. To give you an idea, what does the imagery look like, especially in the 8 bands? This is where near-infrared absorbs all the signature. And then as you can see that with remote sensing, you can actually see very detailed pictures of the sea bottom, and then you can use the slope of that benthic surface to estimate how much energy you can produce from the ocean waves. I think that's the last slide I have. Thank you.
Thank you. Hold on just a second. See, are there any questions, any comments? We're just not doing that today, are we? Okay. We'll get to that later. Our next speaker is, our final speaker is Dr. Geoff Zeiss, principal Between the Poles. As you can imagine, he sometimes suffers from alphabetical bias, and he's ended up the last person on this panel to speak today. And he was very gentle about pointing that out to me, but he didn't realize he was playing with fire. One time I was hosting a conference, and my very best friend in geography complained because he was the last person on the last day. So I took his students in while he was speaking and had them start sweeping the floor and folding the empty chairs. but I won't do that today.
Oh, great, thank you.
Geoff tracks the contribution of spatial technology to the digitization of construction and energy infrastructure. For over a decade, thank you. I've had a dry cough for a few days. For over a decade, he was responsible for thought leadership, evangelization, and industry messaging for the electric power industry program at Autodesk. In recognition of his efforts to increase the awareness of geospatial data and technologies in utilities and construction, Geoff received the Geospatial Ambassador Award at Geospatial World Forum in 2014 in Geneva, Switzerland. He actively supports open standards as the director of the Open Geospatial Consortium. Geoff.
Great, thanks a lot. What I'd like to talk about today is something that's been neglected. This is actually a slide from the FGDC, which is the first time I've seen recognized at the national level that what's under our feet, what's underground, and in general, I'm going to talk specifically about infrastructure, but in general, we're interested in water, groundwater, geology, soils, and so on and so forth, because if you're building things, you need to know those. This is going to be, the fact that we don't know where things are underground is going to be a serious drag on any build out of the electric power industry or water industry or any of our major utilities. And I'm going to give you a little bit of information about why that is the case. Let me just first talk about a project in Australia. This is a light rail extension. It was basically a 5-year project to extend the light rail system in Sydney, in Australia. They spent a year looking for infrastructure, utility infrastructure that was in the right of way, and they found 400 or 500 different utilities. It would be water, gas, electric, and so on. During construction, they found another 500, okay? The result of that was, and they actually brought in a consulting firm to determine what the impact of that was. And on a 5-year project, that consulting firm determined that that project could have been finished a year and a half earlier if they'd known what was underground. If they'd had an accurate model, 3D model desirable of what was underground. So the fact, this is not just a nice to have. This has dramatic impacts on things, and I'll give you a few statistics about this. First of all, risk to the public. The Common Ground Alliance keeps statistics on these things, and over the last 20 years or so, there's been about 2,000 injuries to workers and the public, and there's been almost 500 deaths. So this, not knowing where things underground is not, again, it's not just something nice to have, it has a serious impact on people's lives. The other thing about it is that it's a major drag on the economy. A very conservative estimate is that it's a $50 billion drag on the US economy. You may not know, but in, I think, 2016, there were almost 400,000 utility hits. In other words, somebody digging a hole and hitting something. It might be telecom, it might be water, it might be electric, it might be gas. If it's electric and gas, you could have a real problem, and that's where the deaths come in. Some studies done by universities, these are ROI studies. The one that's most quoted is the one from the University of Penn State that was done in around 2007, which estimated that for every dollar spent on improving our information about what's underground, we're saving, there's $21 in saving. And in Europe, there's a similar kinds of numbers where for every euro invested, that it would save about 60. So this is a very positive ROI, and in most municipalities, having an ROI of 4 or 3 or something like that is considered, wow, that's a real winner. We're talking now about the ROI of 21 or 16. Construction bids, when they put in, they have to account for the risk of what happens when they hit something underground. So if you're building something, it could be a vertical structure, it could be a horizontal structure, and all of a sudden you come across something that can hold up your schedule, it can affect your budget, it can have dramatic effect on people's lives, as I mentioned before, because you endanger workers. So typically, construction bids are inflated by something like 10 to 30% to account for that. It's not that the construction company has to worry about, but that means they have to get the insurance to cover that eventuality. And in the US, the Federal Highway Administration has reported that worrying about underground utilities conflicts and relocations is a major cause of project delays during road construction, which affects everybody. Locate business, in other words, the folks that come out when you call a one-call center. If you're going to dig a hole that's over about a foot or foot and a half deep, you're supposed to call the one-call center, and every state has got a one-call center. It's 3111. You call them up and say, I'm going to dig a hole. You give them basically a polygon, say, this is where I'm going to dig it. And what will happen is 7 vans will descend on your location from utilities, telecoms, and so on with magic wands, and they will paint on the ground, because that's all they're required to do. There's no paper flow at all. There's no digital flow at all. There's paint flow. So you paint on the ground where you think your stuff is, and then after that, you're free to dig. And if you hit something, then it solves your liability problem. So that business of those folks who do that, sometimes utilities, sometimes companies that just do locate, is estimated to be about $10 billion a year annually. And it's a great business, because every time you dig in the same place, you have to call these guys, and they come out and they paint the ground again. They don't even take digital pictures of what they painted on the ground. I mean, it's just over and over. So if you want to invest in a really good business that has a big future, I would say the locate business has got a tremendous future. And this is an example of this is actually from New York City, of what happens when those folks show up. There is some good news. There's some very interesting technology. This is an experiment that was done in Toronto. It was basically a rig that was towed. It had ground penetrating radar array on the bottom. It had LiDAR on the top. It was towed at about 85 kilometers an hour, which is remarkable, because usually when you're using ground penetrating radar, it's a push cart, and you're going about 1 kilometer an hour. This captured data at 85 kilometers an hour, and it captured not only below ground and above ground. When you post-process this in the office, then you can look for above ground things like risers and so on that give you some indication that maybe there's something down there, and you can combine that with your ground penetrating radar scans to put together a 3D model of what's underground. So this is really a major advance. Another one is when you build pipelines. Before you cover the hole, you just take this rig, which you can probably see there on the top, and drive it along. It's got LiDAR on it and a camera and a photo camera, and you capture what we would call digital as-built, and afterwards you can process that stuff in the office if you're looking, for example, for weld points and that kind of thing. There has also been an experiment to use consumer smartphones, that after you expose some infrastructure during a construction project, during an excavation, that you just go out with your smartphone, take a bunch of pictures, upload them to the site, and those then could be shared with other people who may use that kind of information in the future. So that's good news. Another really interesting experiment is just putting GoPros on a backhoe, so that whenever you're digging anything, you just can either take a video or take a couple of stills, upload it to a site, and you've got some very accurate information about below, and it's not lost. So there are some very interesting things going on. This is an experiment that was this is a technology that was first used in Afghanistan for piloting vehicles in areas that were relatively dangerous, and it was basically using ground penetrating radar and capturing it, and then the vehicle, the next time it went through, using that footprint to guide it across. And it would be very useful in places where, like yesterday, you have snow and other things on the ground, where some of the autonomous vehicle technology now is not very good. And of course, you can use augmented reality. You've probably seen this kind of thing before. one of the really important things is sharing this information, and right here in New York City, there's a very interesting effort that's underway. It's called MUDDY, but it's basically putting together a way of exchanging information using open geospatial standards for sharing information about the underground, not just infrastructure, but soil, water, and geology. And the city of Chicago has a pilot underway where using things like taking digital photos of what's underground when you expose something, you can put together 3D models of the underlying infrastructure. Nationally, there's been some very interesting initiatives around the world. France has a program underway to ensure that all critical infrastructure, means basically energy infrastructure, is mapped to 40 centimeters. And that is supposed to be completed by the 1st of January in 2019 for urban areas and 2026 for rural areas. And in the UK, there's an initiative to create a national digital twin, which includes above ground and below ground. And in North America, there's an initiative that was just started earlier this year, I think in May at the Arizona, I actually gave a presentation there about the underground, underground part of this initiative to map everything, all infrastructure above and below ground. Now I'd like to just run a video. I think the folks back there, and this is the kind of thing that I think you'll find quite common. 3D models of the above ground. This is LA. It was actually done for a transportation project, but this is what you don't see, and this is only partial. Being able to not only see all that wonderful stuff above ground to millimeter accuracy, but knowing where things are underground, and this is only showing transportation infrastructure down below. It's not showing all the other stuff that's down below that would actually allow you to do a lot of things. And if you know anything about the UK, then you know that there's been a Crossrail project that built a new rail system right through the heart of London, and they had to have a very accurate 3D model of below ground to do that without hitting something. So just to wrap it up, there is a lot of information about the underground that we don't have and that we need. It has impacts for human health and human safety. It has impacts for the economy, and I think it has a major impact for the cost of developing and expanding our energy grid. We put a tremendous amount of effort into collecting this information every year. $10 billion goes into collecting this information over and over and over again, the same information. And if we could come up with a very simple way of sharing that information, we could rapidly build out a much better knowledge about what's underground. And there are some cities, I didn't go through everybody I know, but I have a list of cities and regions around the world. I mentioned some of the nations, but there's some I didn't mention, that are recognizing the importance of reliable underground information, and they are actually doing something about it now. And I think that it's something that here in North America, we really need to worry about if we're going to have the kind of future energy system that we've been hearing about today. Thank you very much.
Thank you, Geoff. Thank you, Geoff, and thank you all. And we'll open it now to the question and answer period. Try to offer real interaction with the audience. Let me first ask, does anyone have a question for Geoff? All right. And please give your name, Amy.
Amy Glassmeyer from MIT. So you probably heard of the outer suburb explosions that took place in Massachusetts and outside of Boston. Do you think that there'll ever come a period where we'll have penetrating radar so that you can do more than see things, you can actually assess the conditions? Because basically what happened is they put a fitting on an old pipe that allowed more gas than the pipe could hold, and it blew up. And we're now in the city all over where I live thinking, well, it could happen anywhere, because every town was settled, 1730, 1820. Do you think we'll ever have an ability to assess the quality of the technology or the infrastructure underneath?
Yes, I do. In the UK, there's been a 10-year program that just ended, and it was called basically finding things underground. They just renewed it for another 10 years, and that's called assessing the underground. And it's a number of universities, the University of Birmingham in particular, that are looking into technologies that would allow you to do that. Ground penetrating radar is just one of about 10 or 12 different technologies that can be used on the underground. The two most common ones are EMI, which is electromagnetic induction, and ground penetrating radar, but there's magnetometry, and I could list 8 others that could be used to do that. And I think most people believe that we need a smorgasbord, a cocktail of technologies that could be used underground. And I think if you look at things like that are used in medicine, like MRIs and so on, I think that those technologies will be able to be used to do exactly what you have outlined. Not only detect, yeah, I've got a pipe and I know this kind of material, but I can detect there's some corrosion on it and there's a weld point here. I think it's entirely doable. The good news is that I sense that there is some investment going into what I would call the big frontier for remote sensing, which is remote sensing underground. And I know the Maxar guys worry about things in satellites. I think we've got to now take that and start thinking about just looking a couple of meters down below.
And if we had that technology, it would be useful for a lot of other things too, archaeology, paleontology, a lot of things.
How long? I think the technology's there. I think it's applying it. I mean, I think in the next 5 years, we could do this. When people realize how bad, what a drag on the economy and how dangerous it is having stuff underground and not knowing about it, I think things are really going to accelerate. And I detect that people are becoming aware of what this problem is and that it is relatively easily solved.
Jack?
This question may be best for Kumar.
Introduce yourself to the audience.
I'm Jack Eichenbaum. I'm retired. I have a lot of fun. But I've taught geography of New York City in a number of different venues. The question I have may be most easily answered by Kumar, but others of you may have an opinion, so I held it off. In the last 30 years, the cutting edge of commercial architecture has shifted away from things you do to make things easier for the public, building atriums and walking through buildings and connecting to transit, to green architecture. And better window glass, more energy conservation. And I'm thinking of what's happening on rooftops. And I don't know, maybe Kumar can answer this, which produces more energy? Using the sun to create solar energy with solar panels on a rooftop, or farming on the rooftops to produce food?
I don't know the details, but what I can tell you is that I'm looking at Singapore. I go to Singapore often, and they do have both types of those kinds of energy, sustainable energy initiatives. And given that there's not enough sunshine in Singapore, they actually bank on the vegetation being grown on top of the buildings. And actually, Singapore is awesome in the sense that they even have the kinetic energy. When humans walk on the sidewalks, they are actually converting that into energy. So I do not have absolute numbers, but my inclination is solar power will have much more potential than the biofuels in that case.
Next question. Well, I have a question for all of the panelists. I tipped them off ahead of time that I was going to ask this. Early on in this meeting yesterday, I was thinking about the excitement we had with transportation last year. Dean Wise did a fantastic job with that. And we were really challenged to look ahead and think what's going to happen maybe in the 2050 timeframe. In fact, when we originally discussed the name Geography 2050, one of our questions was, would we be able to get people to really put themselves out there and talk about futuristic things that might happen then? I was really gratified to see that this morning. We had it in the first session this morning. So I'm turning to them and asking for whatever niche they are in, what do you envision as the innovation that's worthy of the term 2050? When I mentioned that to them, Geoff said, sensors to look under the ground. So I want to give him time to think of a second one as we go across here. But I'll start with Rod, and you're welcome to come to the podium if you like. But
I think I'll sit here. Yeah, so if from my vantage point, source. That's what Eastview does. 30 years from now, I mean, golly, I don't know where I'll be or what will be going on. But what I do believe, because I already see it happening, and I think Oak Ridge, there's so many examples of it. And 30 years from now, from a source perspective, the global models, underground infrastructure, and so many things that right now are in piecemeal ways, will have been stitched together, and our view, the interdisciplinary, the interconnected view, the access to information to make decisions will be just so realized. And artificial intelligence and machine learning will be playing roles. As someone said, the difference between machine learning and artificial intelligence. I understood that when they said that. Machine learning is training the computers to look through information that we can't do, and then the artificial intelligence layers on insight over that. And so I think the machine learning world 20 years, 30 years from now will have mapped the world underground and above, and there'll be global models of incredible resolution.
Yeah, I mean, I live in the new space economy, if you may. There are a lot of exciting things happening now, but I think 30 years from now, the entire space will become one of your assets. I think it's already an asset for a lot of the nations. And today, the small rockets are able to get your satellites up there much more quickly. In-orbit servicing is something we're looking at. And thanks to some of the initiatives like removing the debris, I think we're making space at least for the satellites, a little more safer than what it is today. But I think it's the edge computing, making decisions in space and communicating the information back to the ground so that people can act on it. I think that will, where I see 30 years from now, should become a commonplace.
Bill?
When I tried to go to my hotel last night, I went 1 mile and it took an hour and a half. So I think there's going to be a sort of a transformation of society and behavior that says, I need to go from point A to point B. That doesn't have to be in a private automobile. So I think there'll be, as society evolves and transforms, we'll see newer ways of having people go from one place to another that doesn't involve the horrendous traffic jams that we saw last night. Another kind of thing, going to the theme of digital transformation and behavior, I think of long-distance transportation. I talked earlier yesterday about maybe looking at more electric freight and also perhaps charge-in-motion systems. In other words, everybody's got a big battery in their car, but maybe the technology, and if you think about wireless electricity as well, you know, you can, in some cases, you can drive your car into a garage and have your electric car charged without wires. So I think charge-in-motion might also be another option that we'll see in the future, where we're using electromagnetic technology to actually power the vehicle without actually having to have a plug-in. So those are possibilities.
So you don't think 30 years from now you'll say, beam me up, Scotty?
Well, I mean, you know, again, we have this idea that things have to be kind of incrementally improved, and perhaps there's new ways that we haven't really thought of, although we still can leverage the existing technology, but we have to apply it to behavior.
A few years ago, we were doing our change detection globally using moderate resolution imagery, and we were doing it on premise, and we could process 300 to 400, even up to about 500,000 Landsat scenes per year by processing on premise. We knew that wasn't going to be our future because it just took too long to do that. Today, we are processing millions of scenes per year, but taking advantage of the clouds. And we're not moving any data anywhere. We're literally putting our algorithms wherever the data reside in the cloud and processing them. So what I see in the future is what we've been doing with moderate resolution because of the size and the scale, we're moving to high resolution imagery. And what I see on that is that every high resolution image taken will be thrown into a cloud detection algorithm, and we'll have tipping and queuing, just like we're doing with tipping and queuing now with moderate resolution, but totally with the high resolution imagery. And that, you know, I don't think it's going to take to 2050, but I think it's going to take 5 or so more years around to do that. And whenever you do that type of high resolution change detection, you have to answer the question, high resolution change detection for. And let me give you an example of that. Live in Germantown, Maryland. I go to a church in Germantown, Maryland. If you take a satellite image, high resolution satellite image of my church on Sunday, and then the following Monday, you're going to take another picture of it, you're going to have change. What's that change? That change is that Sunday we had lots of cars in the parking lot. Monday we didn't have any. And if that's not the type of change you're looking for, that doesn't answer change for, then you've given false alarms just because that change, unless you were actually looking to count the cars in our parking lot, that change was meaningless. So yes, where we have to be going is to do that type of things we're doing with moderate resolution, with high resolution imagery, and we have to have it focused on answering the question you want the change detection for.
Thank you. Geoff, did you come up with something else?
Yeah, I did. Yeah, so the first one was the one I already mentioned to you, which is, you know, better technologies, right along with the, you know, along the lines of the question, better technologies for detecting things underground. The other thing I would really like is just being able to share the location information that we're capturing over and over and over again. I mean, it's not a technical problem. It's a very simple technical problem. But, you know, instead of just painting things on the ground, at least take a digital picture of it or something so that you can share it or upload it somewhere and it could be shared, you know, with everybody else who's going to be doing work in the same area.
I think we have one question from the audience.
To play off the comment that you just had, I think it's important to look at that over and over stuff, but it's also important to look at the legacy things, and perhaps we do need to digitize analog maps and look at old features that have been there for decades, if not centuries. I mean, subway systems have been around since the turn of the century or before. They are not digitized, all right? Any of the information that relates to those is actually pace counts against a survey. We have onion skin maps. We have a fruit salad of different kinds of geospatial reference points that all give us a cornucopia of information. But frankly, we're turning to purely looking at technology and doing surface skin scanning and LiDARs in order to go ahead and get our formulation of how this works. That's wonderful, but it doesn't capture a tenth of what's out there.
Anyone have a comment?
Yeah, one of the things I talk about is the concept of data curation. Today, if you look at some of the numbers from World Bank, 80% of the global population do not have digital land records. The keyword is digital land records. And you can't just say you're going to start from fresh. I'm a civil engineer by education, and the way we did our parcels was go to that tree, walk 10 yards to northeast. So you absolutely have to go back to those maps to bring it up to date. And one of the interesting things is that our older generation satellites of DigitalGlobe, QuickBird and Iconos, they were 20 meters off in terms of positional accuracy. The WorldView satellites are coming to 1 meter. Even with our satellites, I could be 1 meter to the left today, 1 meter to the right tomorrow. And on top of it, the plate tectonics. The earthquake that happened in Japan rotated the island by 8.5 feet. I honestly think a lot of the technologies of map making are obsolete. We got to rethink location. How are you going to represent the location? And there is the relative aspect of it as well. So when you have multiple data sources, that could be the ground penetrating radar or GPS imagery, it doesn't matter. we have to step back and look at a different architecture on the digital twin or representing the Earth in 3D and eventually 4D, because things are changing very, very quickly. And when somebody talks about, apologize, 1 to 50K maps, it was when Christopher Columbus had a piece of parchment to put some data, that's where the scales come from. That concept, in my opinion, is gone. We need to rethink the concept of mapping. The word map we all associate with, but in my opinion, we are at a point where we are actually moving from what I call a data poor paradigm to data rich paradigm. Quick example, civil engineer, I would have a theodolite or laser to take 10 elevation points and would create an elevation model. Now you have a terrestrial LiDAR that can sit in this room and collect 1 billion points in an hour, and we still use contours. I think we are at a point where we got to rethink the entire concept of mapping, how we're doing it today.
If I may add to that, I've been working in Central America for 5 years now on a project where we help indigenous cultures map their own resources, their own land, their own use rights, so that they can defend them from encroachers. And we use participatory methods. It would be impossible to pay the cost of doing it any other way. We send them out, work with them, go out with GPS units and map. And there we're not just talking about a boundary, we're talking about a use right that says this village has a right to that tree, that forest, and that pond, and that place to gather eggs. It's a very complex interleave system, and there's no other way. You couldn't do it by paying someone to go do it as we've done traditionally.
I just have a quick comment, and I actually agree a lot with what Geoff said about data sharing. And I think that we're really poor at that, and it just reminds me of a story. When I worked for the power company, we used to dig all the time. We'd dig a trench across the street. And we always had this bad habit of digging the trench the day after the city paves the street. And the reason we did that is because we didn't have the infrastructure to be able to share. And that's where sharing of GIS information becomes so critical, once that data is there.
All right, thank you. Do we have time for one question?
Alan Leidner, Director of Geospatial Innovation for the Fund for the City of New York, and working on the underground infrastructure project. I just wanted to mention here, for that project and for many others, the importance of data standards that are being put out by the Open Geospatial Consortium. We could not possibly hope to integrate the data from all the underground utilities and the city utilities without the standards that OGC is developing, nor could we connect the underground infrastructure with the above-ground city GML to model the entire environment. So never forget the importance of standards and the OGC role in it.
Thank you very much. I think it's important to recognize that among our panelists today, everyone has been talking about two things: some real Earth system that needed to be monitored and a methodology for monitoring that. They've done a wonderful job with it, and I thank them for that. Ever since we started, our first meeting was on the question of the future of geography, and I think with each of these domains, we've gotten closer and closer to answering that question. Thank you. And thanks to our panel.